So this time I'm going to look at Volume 2 of the Intel Software Developers Manual. Specifically, I'm going to look at Chapter 2, because that's all about the instruction format. Chapter 3, because that includes some stuff about interpreting the instruction reference pages. And then maybe a bit of Appendix A and definitely Appendix B, because Appendix B also includes some stuff about the machine instruction format and the general purpose instruction formats. So I think that Chapter 1 here is basically just an overview of the volume. So we'll just skip that and go straight to Chapter 2. Before I start that though, there was one note that I forgot to take down while I was going through Volume 1, and that is basically that the SP register can't be used as an index. Let's just go to Chapter 2, Instruction Formats. This chapter describes the instruction format for all Intel 64 and IA32 processors. The instruction format for protected mode, real address mode, and virtual 8086 mode is described in Section 2.1. Increments provided for IA32E mode and its submodes are described in Section 2.2. So basically we'll just sort of read this top to bottom and skip anything about floating point and SIMD, because I'm just focusing on general integer programming at the moment. So the Intel 64 and IA32 architecture's instruction codings are subsets of the format shown in Figure 2.1. Instructions consist of optional instruction prefixes in any order, primary opcode bytes up to 3 bytes, an addressing form specifier if required, consisting of the ModR byte and sometimes a SIB, scale index base byte, a displacement if required, and an immediate data field if required. So this is the diagram here. We've got the optional prefixes, the opcode itself, the mod and SIB if they're required, and the displacement and immediate if they're required. It looks like ModRM is basically split up into 3 fields. So there's a 2-bit field here, a 3-bit field here, a 3-bit field here, and then SIB is also the same with 2-bit, 3-bit, 3-bit. ModRM, okay, it goes mod, then reg, opcode, then RM. And then SIB is in the same order as the initials here. Scale, index, and then base. The REX prefix is optional, but if used, must be immediately before the opcode. Okay, that's fine. Instruction prefixes. Instruction prefixes are divided into 4 groups, each with a set of allowable prefix codes. For each instruction, it is only useful to include up to 1 prefix code from each of the 4 groups. Groups 1 through 4 may be placed in any order relative to each other. So we've got group 1 is lock and repeat prefixes, so the lock prefix is encoded with F0. I think we saw lock in the beginning of Chapter 7 of Volume 1 about general programming. And that was in the context of compare exchange. So I assume in that case, if you wanted to explicitly make sure it was locked, because I think what it said was that if compare exchange accesses a memory operand, then the lock is automatically asserted, but I assume that if that's not going to happen, you would want to put, for example, this prefix on the instruction to make sure that it does assert the lock. Maybe. That's my guess anyway. Repeat instructions, repeat prefixes are encoded with F2 and F3, and they apply to string input and output. F2 and F3 also used as mandatory prefix in some instructions. So then we've got BND prefix, we've got segment overrides in 64-bit. So in IA32E 64-bit submode, CS, SS, DS, and ES are all treated as 0, so I assume those won't really matter. But FS and GS can still be used, although I'm treating them as basically reserved by the operating system. Then we got branch hints with a little note attached to it. So the note is that microarchitectural behavior varies, so we're not going to worry about that. Group 3 is Operand-size override prefix, which is encoded using 66, but that's also a mandatory prefix for some instructions. And then 67 is the address size override prefix. The lock prefix forces an operation that ensures exclusive use of shared memory in a multiprocessor environment. Repeat prefixes cause an instruction to be repeated for each element of a string. Use these prefixes only with string and I/O instructions, MOVS, COMPS, etc. Use of repeat prefixes and or undefined opcodes with other Intel 64 or IA32 instructions is reserved. Such use may cause unpredictable behavior. Some instructions may use F2 or F3 as a mandatory prefix to express distinct functionality. Branch hint prefixes allow a program to give a hint to the processor about the most likely code path for a branch when used on a conditional branch instructions, JCC. The operand-size override prefix allows a program to switch between 16 and 32-bit operand sizes. Either size can be the default. Use of the prefix selects the non-default size. For example, if we're running in IA32, so if we're running in IA32 E in the 64-bit sub mode, the code segment's D flag specifies that the operand size is 32 bits by default. We can bump this up from volume 1. It said that we can bump this up to 64 by using rex.w, and that rex.w would actually take precedence over an operand size override. So if operand size override is actually, what are we saying, 66 here? Then what I would assume is that even in IA32E 64-bit submode, since cs.dflag, the code segment dflag, specifies operand size's default as 32-bit, I assume that if we did OX66 on the beginning of an instruction, or before an opcode, that would bump us down to 16-bit operands. And then we would use rex.w if we wanted to get the 64-bit, where rex.w takes precedence over the operand size override. Some SSC instructions and instructions using 3-byte sequence of primary opcode bytes may use 66 as a mandatory prefix to express distinct functionality. Other use of 66 is reserved, unpredictable behavior, and then we got address size override, which is 67, and this allows programs to switch between 16 and 32-bit addressing. Either can be the default, the prefix selects the non-default size. So this is talking about IA32, which is why there's 16 and 32-bit addressing. In IA32 E64-bit, the cs.d flag specifies that the address size is 64-bit. So in this case, if we did OX67, my assumption would be that that would bump us down to 32-bit addresses. So if we wanted to use, for example, EAX as the memory address, we would probably have to use this as the prefix to the instruction, because the default should be, for example, RAX in a 64-bit mode. So opcodes. A primary opcode can be 1, 2, or 3 bytes in length. An additional 3-bit opcode field is sometimes encoded in the ModR byte. Smaller fields can be defined within the primary opcode. Such fields define the direction of operation, size of displacements, register encoding, condition codes, or sign extension. Encoding fields used by an opcode vary depending on the class of operation. 2-byte opcode formats for the general purpose and SIMD instructions consist of the following, or one of the following. An escape opcode byte OF as the primary opcode and a second opcode byte, a mandatory prefix like 66, F2 or F3, followed by an escape opcode, and then the second opcode byte, which is the same as the previous one. So in the example of this instruction here, that is the sequence of this mandatory prefix, followed by an escape, followed by an opcode. So I assume that this opcode, this escape here, is basically to signal to the processor that it needs to interpret a multi-byte instruction of some kind. 3-byte opcodes, same thing, but it can just have two. It can have two additional opcode bytes after it. So actually, the 2-byte opcode can actually be up to 3 bytes, and the 3-byte opcode can actually be up to 4 bytes in length. Valid opcode expressions are defined in appendices A and B. ModR, M, and SIB bytes. Many instructions that refer to an operand in memory have an addressing form specifier byte called ModR M byte. Following the primary opcode, the ModR M byte contains 3 fields of information. The mod field combines with the RM field to form 32 possible values, 8 registers, and 24 addressing modes. So yeah, 8 and 24 is 32. So that means that if we've got the 2-bit mod field plus the 3 bits RM field, that's 5 bits. So if we've got 2 to the 5, that is 32. So we've got 32 combinations of values, 32 possible values. So if that is relating to 8 registers, for example, 2 to the 3 is 8, so that would be the selection of one of the general purpose registers. And then the mod field here is 2 to the 2, which is 4, so we've got 4 different modes that we can be in. So we've got 4 different modes, and then the 8 different registers that we could select from. Yeah, I assume that that is basically 32 different selections. Yeah, that's it. 32 different selections, right? So we've got 8 multiplied by 2 is 16, multiplied by 2 is 30. So that's where all of those values come from. The reg opcode field specifies either a register number or 3 more bits of opcode information. The purpose of the reg opcode field is specified in the primary opcode. The RM field can specify a register as an operand, or it can be combined with the mod field to encode an addressing mode. Sometimes certain combinations of the mod field and the RM field are used to express opcode information for some instructions. So a lot of it just depends on the instruction, I guess. Certain encodings of the ModR M byte require a second addressing byte, the SIB byte. The base plus index and scale plus index forms of 32-bit addressing require the SIB byte. The SIB byte includes the following fields. We've got scale, which is the scale factor, the index, which is the register number for the index, and then we've got a base register as well. So that makes sense as the scale being the 2-bit field, because from volume 1 I think we said that the scale can basically be, yeah, so the 2 to the 2 is, so we get the 4 options, and that's because the scale can be one of either 0, 2, 4 or 8. So we've got 4 different options here, and that's what each of these combinations represent. Then we've got a 3-bit field for each of the registers, and since 2 to the 3 is 8, that gives us the numbering for the GPRs. So that's the AX, CX, DX, BX, and the SI, DI, BP, and SP registers. Okay, displacement and immediate bytes. Some addressing forms include a displacement immediately following the ModR M byte, or SIB byte if one is present. If a displacement is required, it can be 1, 2, or 4 bytes. And if an instruction requires an immediate operand, that's the same thing, it just comes after the displacement bytes. Addressing mode encoding of ModR, and SIB bytes. The values and corresponding addressing forms of the ModR, and SIB bytes are shown in Table 2.1 through Table 2.3. 16-bit addressing forms specified by the ModR byte are in Table 2.1, and 32-bit addressing forms are in Table 2.2. So we're going to ignore Table 2.1. Table 2.3 shows 32-bit addressing forms specified by the SIB bytes. So if we have a SIB byte following, we need to use Table 2.3 to encode that. In cases where the reg opcode field in the ModR byte represents an extended opcode, valid encodings are shown in Appendix B. In Table 2.1 and Table 2.2, the effective address column lists 32 effective addresses that can be assigned to the first operand of an instruction by using the ModR fields of the ModR byte. The first 24 options provide ways of specifying a memory location. The last 8, where mod is 1.1, provide ways of specifying general purpose registers, MMX technology, and MMX registers. So if we go down and look at the table, this is Table 2.2. So here we've got the different, so this is the effective address column. So if mod is 1.1, that gives us access to general purpose registers. Anything else gives us access to memory locations, specified by some value in a register. So this is like dereferencing a pointer in this case. So that's where the 2 bits of mod and the 3 bits of this give us the 2 to the 5, which is the 32 different options that we've got running down here. So if we wanted to encode EAX, that would be 11000 for the first operand of an instruction. Let's see. The mod and RM columns in Table 2.1.2.2 give the binary encodings of the mod and RM fields required to obtain the effective address listed in the first column. For example, see the row indicated by mod 11 RM000. This identifies the general purpose register EAX, AX, or AL, which is what I just went over. The register used is determined by the opcode byte and the Operand-size attribute. So I guess this basically means that if the opcode needs a general purpose register, it's going to choose one of these. And if it needs a floating point or SIMD or something, it's going to use one of these. And then I guess within that, if we're using an instruction that or if the cs.d, for example, says that we're in like a 32-bit operand mode, the default would be to use EAX, and if we used like OX66, that would select the 16-bit one. And I think that the byte ones might just have their own instructions. So that's how it selects those. Now look at the 7th row in either table, labeled reg equals. This row specifies the use of the 3-bit reg opcode field when the field is used to give the location of the second operand. The second operand must be a general purpose MMX technology or XMM register. Rows 1 through 5 list the registers that may correspond to the value in the table. Again, the register used is determined by the opcode byte along with the operand size, the same as what we just explained. If the instruction does not require a second operand, then the reg opcode field may be used as an opcode extension. This use is represented by the 6th row in the tables labeled /digit opcode. Note that the values in row 6 are represented in decimal form. The body of table 2.1 and table 2.2 contains a 32 by 8 array that represents all of the 256 values of the ModR M byte and hexadecimal. Bits 3, 4, and 5 are specified by the column of the table in which a byte resides. The row specifies bits 0, 1, 2, and bits 6 and 7. So this is bits 6 and 7, this is bits 0, 1, and 2, and then this is bits 3, 4, and 5. And those all combine together to give us C8. So C8 in the table is here. So C8 would specify that the first operand, assuming that we're in 32-bit operand size, the first operand would be EAX, and the second operand would be ECX. So that's how we use this table. So that's basically, so in binary it's 001, and then the slash digit thing, this would be, we would have to use this if we were extending an instruction instead of selecting a register. Let's just carry on reading. The hyphen nomenclature means a SIB byte. A SIB follows the ModR M byte. The DISP32 nomenclature denotes a 32-bit displacement that follows the ModR M, and DISP8 does the same thing, but for an 8-bit displacement. So if we somehow ended up encoding this with mod 01 and then 100, this hyphen thing here means that we would also need to generate a SIB byte using this table instead. I think maybe we'll come back to this and try and maybe we'll try and manually encode some instructions and see if we get it right later. So in the SIB table, the asterisk nomenclature means a DISP32 with no base if mod is 00. Otherwise, it means DISP8 or DISP32 with EBP. So that would, EBP would be the base because it's adding the displacement. This provides the following address modes. So if it's 00, it's the scale index plus this. 01 and 10 is scale index with different displacements plus these two as the base. So in these these are two special cases where EBP is the base, I guess. Cause the asterisk up here is where EBP would be. So in the case of EBP, it is so if you wanted to encode EBP as the base in 00, I wonder how that works then. So if it's 00 as the mod bits, the effective address is the scaled index plus a DISP32. So how do you do EBP as a base? Oh, okay, up here we've got EBP as a base plus a displacement. So I guess the base register is sort of a combination of this table and the SIB table. And the SIB table is more required, I guess, if we're doing an actual scale. Because, for example, if we just wanted to, say, add some displacement to an EDX base that has just a single mod RM byte here, and it doesn't require the SIB at all in that case. So I suppose scaled index is where things really start to require SIB. Okay, IA32E mode, which is what we're going to be running in. IE32E mode has two submodes. These are compatibility mode and 64-bit mode, which is what we're going to be running in. REX prefixes. REX prefixes are instruction prefix bytes used in 64-bit mode. They do the following: specify GPRs and SSE registers. They specify a 64-bit operand-size and specify extended control registers. Not all instructions require a REX prefix in 64-bit mode. A REX prefix is necessary only if the instruction references one of the extended registers, so that will be registers R8 to R15, or one of the byte registers SPL, BPL, SIL, and DIL, and that was because in volume 1 we saw that the REX prefix was required to access these. If you don't use a REX prefix, you end up with, you know, AH, BH, CH, and DH. Or uses 64-bit operand. So basically, if we want to access R8 to R15, or we want to access one of these low bytes, or if we want to do a 64-bit operation, then we need to use a REX prefix. A REX prefix is ignored, as are its individual bits, when it is not needed for an instruction, or when it does not immediately precede an opcode byte or the escape opcode byte of an instruction for which it's needed. This has the implication that only one REX prefix properly located can affect an instruction. When a REX prefix is used in conjunction with an instruction containing a mandatory prefix, the mandatory prefix must come before the REX, so the REX can immediately precede the opcode or the escape byte. For example, this instruction with a REX prefix should have a REX prefix placed between F3 and OF. So this would be the mandatory prefix, and then OF here is the escape opcode. So the REX needs to go in the middle of these. Other placements are ignored. The instruction size limit of 15 bytes still applies to instructions with a REX prefix. So there's a limit of 15 bytes. And this is basically the order in 64-bit mode. So I think I'll note this down. So basically the order for an instruction encoding is we have prefixes, then we have the opcode, then after the prefixes we have a REX if needed, then we have the ModRM, then we have the SIB, then we have a displacement, and then we have an immediate. So they must go in this order, and what did it describe it as? It's an instruction size limit is 15 bytes, even with REX. Okay, so those are a few things that we can keep in mind and check for in the code generation. Okay, so let's see, encoding. Intel 64 and IE32 instruction formats specify up to 3 registers by using 3-bit fields in the encoding, depending on the format. ModRM, the reg and RM fields of the ModRM bytes. ModRM with SIB is the reg field of the ModRM byte, the base and index fields of the SIB byte. Instructions without a ModRM is the reg field of the opcode. Okay. In 64-bit mode, these formats do not change. Bits needed to define fields in the 64-bit context are provided by the addition of REX prefixes. More on prefix. Maybe I should note these things down as well. So let's see, we've got if mod rm exists, or if mod rm is used to select registers, then use reg and rm fields. If mod rm and SIB is used to select registers, then it's the then use reg, base and index, and if no mod rm is used to select registers, then use the reg field of the opcode. Okay. So more on REX prefix fields. REX prefixes are a set of 16 opcodes that span one row of the opcode map and occupy entries 4, 0 to 4f. So that's because we saw that the REX prefix is, I think this was in volume 1 as well. The REX prefix is basically 0100 followed by some other bits. So we have the low nibble here. So this is always 4. And this could be anything from 0 to f. So that's why it's the range 40 to 4f is what the REX prefix covers. These opcodes represent valid instructions in IA32, so inc and dec are actually encoded using these in IA32 operating modes and in compatibility mode of IA32E. In 64-bit mode, the same opcodes represent the instruction prefix REX and are not treated as individual instructions. The single byte opcode forms of inc-dec instructions are not available in 64-bit mode. Inc-dec functionality is still available using ModRM forms of the same instructions, which are opcodes FF/0 to and FF/1. See Table 2.4 for a summary of the REX prefix format. Figure 2.4 and through Figure 2.7 show examples of REX prefix fields in use. Some combinations of REX prefix fields are invalid. In such cases, the prefix is ignored. Some additional information follows. Setting REX W can be used to determine the operand size, but does not solely determine operand width. Like the 66 size prefix, 64-bit operand size override has no effect on the byte-specific operations. For non-byte operations, if a 66 prefix is used with a REX W equals 1, then 66 is ignored. That was mentioned in volume 1. If a 66 override is used with a REX and REX W is 0, the operand size is 16. Also, we saw that in volume 1. REX R modifies the ModRM reg field when that field encodes a GPR, SSE, controller, debug register. R is ignored when ModRM specifies other registers or defines an extended opcode. XBit modifies the SIB index field. And REX B modifies either the base in the ModRM RM field or SIB base field. Okay. It modifies the opcode reg field used for accessing GPRs. So here's some diagrams. We've got okay, the high nibble is basically fixed at the number 4. Then it goes W, then it goes R, then it goes X, then it goes B. Okay. And the way that this works is that the R bit will extend the reg, in this case. The B one will extend the RM, so these end up as being high bits. So this would give us 2 to the 4, which is 16, which would give us all of the GPRs in 64-bit mode, because we have, we've got, AX, we've got CX, we've got DX, we've got BX, SI, DI, BP, and SP. And then we also have R8 through to R15. So these additional 8 GPRs plus, plus these 8 GPRs means that we've got 16 registers to choose from. So this extension with the REX prefix allows us to select any of the 16 registers. And then W specifies if we want 64 bits. So this is just in different situations, what do they extend? So it looks like these two are the same. X is not used. So if there's a SIB byte, then X is used to extend the index of the SIB byte. And the B goes over instead to the base of the SIB byte. And R stays with the register. So it looks like R stays with the register the whole time. W is just 64 bits all the time. X is only used for the index, and then base is the one that can change around a bit. So base is either RM, or if there's a SIB byte, then it's the base in the SIB byte. Oh, and we've got an opcode with a reg field here that B is used for as well. So if we've got a reg in the opcode, that also uses B. Okay, so in the IA32 architecture, byte registers so all of the bytes ones for the the 4 named registers are encoded in the ModR bytes reg field. The RM field or the opcode reg field as registers 0 through 7. REX prefixes provide an additional addressing capability for byte registers that makes the least significant byte of the GPRs available for byte operations. Certain combinations of the fields of the ModR byte and the SIB byte have special meaning for register encodings. For some combinations, fields expanded by the REX prefix are not decoded. Table 2.5 describes how each case behaves. So these are special cases of REX encodings. Okay, so the asterisk means don't care about the value of REX B. So ModR byte REX prefix adds a 4th bit which is not decoded because we don't care about it. Okay. Let's see, REX prefix SIB byte also required for R12 based addressing. Compatibility mode, operation. Okay. Certain combinations of the fields of the ModR and SIB bytes have special meaning for register encodings. So if we got ModR with the subfield of mod is whatever, so mod is whatever, I guess, or and RM is 100. REX prefix adds SIB byte also required for R12. Mod is 0 and then BP. Okay, I think I'll have to come back to this implications table when I actually start encoding things. SIB byte, index is this, index register not used, ESP cannot be used as an index register. REX prefix adds a 4th bit B, which is decoded in this case. There are no additional implications. The expanded index field allows distinguishing RSP from R12, therefore R12 can be used as an index. Right, because R12 would be this lower 3 bits plus the X would be 1. So if index equals 100 and rex.x equals 1, that would give us 1100, which I think would be R12. So in this case, we can use R12 as an index. We just can't use 0100. So if this was x, x is 0, for example, this would equal RSP, which we can't use. So the ModR m byte, if mod is 0, that is memory access. And in the case of memory access, where we've got some B in REX that would extend it, that is not decoded. Using RBP or R13 without displacement must be done using mod 1 with a displacement of 0. Okay, these seem like important things that I should be noting down. So in the case of a ModR m byte, I don't know what it means by this mod question mark though. Subfield encoding question mark, SIB byte present. SIB byte required for ESP addressing modes REX prefix adds B, which is not decoded. SIB byte is also required for R12 based addressing. Okay, I think I'm not exactly sure what it's meaning by mod question mark here. But basically, if oh, that's because, okay, so 100 is ESP. I think this was the case of the hyphen nomenclature, where it was talking about requiring a SIB byte for this. So a SIB byte is also required for R12 based addressing. So let's go back up to the tables quickly and see if we can figure this out. So if I wanted to do R12, which would be BP with the B equals 1, and I wanted to do mod, it said 1 here with 100, that's SP. Maybe the question mark means anything other than 1. So if it was 10, 100, that requires a SIB. So we don't have SP here, which means that we can't encode R12 there. So we have to use a SIB byte in the case of R12, which would be this one here. So we'd have to say we don't want the scale index, so we'd do 00, 100, and then we would do 100 here, which would give us the hex 24. So I think in order to use R12, because R12 would be ESP with the B with rex.b set to 1, that would give us R12. So if we want to use R12 to access memory, we actually require a SIB byte. So there are just a few awkward encoding cases, basically. I am not going to copy out that table, but I will note it down. So this is a refer to Vol 2 Chapter 2 Section 2 IA32E mode. Table 2.5 special encoding, special cases of REX encodings when encoding R12, R13, and RSP, let's say. I think that would cover all of them. So it mentions R12, it mentions R13, RBP as well, we'll just note that. RBP. Yeah, okay. We'll come back to this when we actually start encoding stuff. So displacement, addressing in 64-bit mode uses existing 32-bit ModR, M, and SIB encodings. The ModR, M, and SIB displacement sizes do not change. They remain 8 bits or 32 bits and are sign extended to 64 bits. Okay, so displacements are only 32 bits or 8 bits. Direct memory offsets. Direct memory offset MOVs. In 64-bit mode, direct memory offset forms of the MOV instruction are extended to specify a 64-bit immediate absolute address. This address is called a MOFset, M offset. No prefix is needed to specify this 64-bit memory offset. For these MOV instructions, the size of the memory offset allows the address size default. Direct memory address or memory offset MOVs don't require a prefix for 64-bit absolute addresses. Okay, so if we had MOV, so the opcode A0 is for MOV AL from a direct memory offset, and in this case we don't require a prefix, and the same for these other ones as well. These look like special cases though, so maybe we won't actually get to them anytime soon. Immediates in 64-bit mode, the typical size of immediate operands remains 32 bits. When the operand size is 64 bits, the processor sign extends all immediates to 64 bits prior to their use. Support for 64-bit immediate operands is accomplished by expanding the semantics of the existing MOV. These instructions, opcodes B8 to BF, move 16 bits or 32 bits of immediate data into a GPR. When the effective operand size is 64 bits, these instructions can be used to load an immediate into a GPR. A REX prefix is needed to override the 32-bit default operand size to 64-bit operand size. For example, so here we've got 4 8s, so we know that REX, this must be REX here. So that's going to be, 0 1 0 0, which is the 4, and then we've got an 8, which is the 1 0 0 0, and the first bit is W, so this is basically REX prefix specifying a 64-bit operand size. B8 is the opcode that's mentioned up here. And then we've got, I assume that this is basically 64 bits. So, we've got 1, 2, 3, 4, 5, 6, 7, 8 bytes. So that's 64 bits. And that encodes to a MOV RAX. So this will be the 64 bits. So this is how we know it's 64-bit destination is because it's RAX, and then we've got the 64 bits encoding, or the 64-bit immediate here. So RIP relative addressing, a new addressing form RIP relative to instruction pointer addressing is implemented in 64-bit mode. An effective address is formed by adding displacement to the 64-bit RIP of the next instruction. In IA32 architecture and compatibility mode, addressing relative to the instruction pointer is available only with control transfer instructions. In 64-bit mode, instructions that use ModRM addressing can use RIP relative addressing. Without RIP relative addressing, all ModRM modes address memory relative to 0. RIP relative addressing allows specific ModRM modes to address memory relative to the 64-bit RIP using assigned 32-bit displacement. This is mentioned in Volume 1 as well. This provides an offset range of plus or minus 2 GB from the RIP. Table 2.7 shows the ModRM and SIB encodings for RIP relative addressing. Redundant forms of 32-bit displacement addressing exist in the current ModRM and SIB encodings. There is one ModRM encoding and there are several SIB encodings. RIP relative addressing is encoded using a redundant form. In 64-bit mode, the ModRM disp32 encoding is redefined to be RIP plus 32 rather than displacement only. So if we want to do RIP relative addressing, that is basically ModRM disp32, which is this one. So we do mod 00 and then RM is 101, which is none. And that would give us the disp32, which is in 64-bit mode, that is RIP relative. In 64-bit mode, if one wants to use a disp32 without specifying a base register, one can use a SIB byte encoding indicated with ModRM equals 100. Okay. Okay, I assume that for RIP relative, we'll just stick with this encoding. The ModRM encoding for RIP relative addressing does not depend on using a prefix, specifically the RM bit field encoding of 101B. Used to select RIP relative addressing is not affected by the REX prefix. For example, selecting R13, where rex.b is 1 and RM is 101 with mod 00 still results in relative addressing, which is why to do R13 we need the SIB byte to do that. The 4-bit RM field of rex.b combined with the ModRM is not fully decoded. In order to address R13 with no displacement, software must encode R13 plus 0 using a 1-byte displacement of 0. So we'll just copy this out as well. RIP relative addressing is enabled by 64-bit mode, not by 64-bit address size. The use of address size prefix does not disable RIP relative addressing. The effect of the address size prefix is to truncate and 0 extend. Okay. Okay, let's just copy this out as well into here. Default 64-bit operand size in 64-bit mode. Two groups of instructions have a default operand size of 64 bits. They do not need REX prefixes for this operand size. These are near branches, all instructions except far branches that reference the RSP. I'll just copy that out as well. Additional encodings for control and debug registers in 64-bit mode. More encodings for control and debug registers are available. The rex.r bit is used to modify the ModRM reg field when that field encodes a control or debug register. These encodings enable the processor to address CR 815, DR 815. An additional control register is defined in 64-bit mode. Okay. Well, I'm not going to be using those, so that's fine. Advanced vector extensions is getting into SIMD and things, so we'll just skip over that. I think the rest of these chapters now are more related to SIMD and floating point and stuff, so we'll go straight to chapter 3 now. This chapter describes the instruction set for the Intel 64 and IA32 architectures in IA32E, protected, virtual 8086, and real address modes of operation. The set includes general purpose x87 FPU, MMX, SSE, and system instructions. See also chapter 4. For each instruction, each operand combination is described. A description of the instruction and its operands, an operational description, a description of the effects of the instructions on flags in the eFlags register, and a summary of exceptions that can be generated are also provided. So interpreting the instruction reference pages. Instruction format. The following is an example of the format used for each instruction description in this chapter. The heading below introduces the example. The table below provides an example of a summary table. So we've got some tables here, and they have various headings and stuff. So let's just go back down here. Opcode column. So we're talking about the first column here. The opcode column in the table above shows the object code produced for each form of the instruction. When possible, codes are given as hexadecimal bytes in the same order in which they appear in memory. Definitions of entries other than hexadecimal bytes are as follows. So NP indicates that the use of 66, F2, and F3 prefixes beyond those already part of the instruction opcode are not allowed within the instruction. Such use will either cause an invalid opcode exception or result in the encoding of a different instruction. So I guess the NP here is probably like no prefix. NFX is the same thing but with just the F ones, so no F prefix. REXW indicates the use of a REX prefix that affects the operand-size or instruction semantics. The ordering of the REX prefix and other optional or mandatory instruction prefixes are discussed in Chapter 2. Note that REX prefixes that promote legacy instructions to 64-bit behavior are not listed explicitly in the opcode column. If we see /digit, a digit between 0 and 7 indicates that the ModRM byte of the instruction uses only the RM register or memory operand. The reg field contains the digit that provides an extension to the instruction's opcode. So if we had an opcode like, I don't know, 50, and we saw /2, we would have to encode 2 as reg. So this is between 0 and 7, which is 2 to the 3, because that's 8. So we'd have 3 bits that we encode 2 as. That would be 0, 1, that would be 1, 0, 0. Oh no, 0, 1, 0. So that would be 2, and then we would add that to this. So the opcode would actually become 52. In that case, that would be the final opcode that we generate if we saw /2. /r indicates that the ModRM byte of the instruction. Oh wait, the reg field contains the digit. There will be an extension to the instruction's opcode. Yeah, so I think this must be like the lower 3 bits, I assume, of the opcode. So /r indicates that the ModRM byte of the instruction contains a register operand and an RM operand. Okay. CB, CW, CD, CP, CO, and CT, a 1-byte, 2-byte, 4-byte, 6-byte, 8-byte, or 10-byte value following the opcode. This value is used to specify a code offset and possibly a new value for the code segment register. Probably won't need to be doing this, but I assume that B is byte, W is word, D is double word. So that's 1, 2, 4. 8 here must be oct, so oct for 8. And then 6-byte and 10-byte. Oh, this is related to code segments. I wonder if this is basically related to far pointers. So maybe like T could just mean 10 because it's 10 bytes, and then P could mean pointer because it's related to a far pointer. Because far pointers are basically a 16-bit selector followed by some address, which could be 32, or it could be 16 and 64. So in this case, that's 8 bytes plus 2 bytes is 10. And then in this case, it's 2 bytes plus 4 bytes is 6. So this 6-byte one, I assume that CP is basically, what's it called? Code offset pointer. And this one must be code offset 10-byte pointer or something. Then we've got IW, ID, and IO. So again, I think that's basically byte, word, double, word, and oct. Or byte, word, double, and oct. I don't know. In either case, it's the same thing. So word being 16, double word being 32, and then oct being 64 bits. So I is immediate here. Operand the instruction that follows the opcode. ModR m bytes or scaling index bytes. The opcode determines if the operand is a signed value. All words, double words, and quad words are given with the low order byte first. Yeah, so that's because it's little endian. So plus RB, plus RW, plus RD, plus RO. Again, we've got B, W, D, and O. But we've got plus R indicate the lower 3 bits of the opcode byte is used to encode the register operand without a ModR m byte. The instruction... Oh, okay. I've got these two mixed up then. So digit here... Oh, okay. Yes, I see. Right. So if, for example, we had an opcode of 50 and we saw 2, we said that that's, 010. This should be the ModRM reg field in the ModRM that comes after the opcode here. Then in this case, where we see plus R something, that is... that corresponds with the low 3 bits of the opcode, like I got mixed up with over here. So this would actually be if we had an opcode of 50 and saw, if we had 50 and we saw plus, I don't know if, I assume that the actual size of this doesn't necessarily matter. If we saw plus R something, so like plus RO, then we would have to select the register by using... Oh, this is probably like the register size that's allowed or something. So if we see plus RO, we can select a 64-bit register where REX B can be used to extend it. So this would be, for example, if we did 000, that would be EAX. And then if we put the 1 on the front, which would be the REX .B, that would give us R8, I think. So we would basically extend this with zeros. So in this case, 50 plus 0 is still 50, right? Maybe that was a bad example. If we had ECX, for example, that would be 1, so it would be plus 1 here. So it would end up as an opcode of 51. And then we could put a REX, rex.b 51 would give us R9, maybe, I think. So basically we encode the register we want in the opcode itself if we see plus something. And we can extend to use the 64-bit stuff with REX-B. Yeah. Plus RO is only applicable in the 64-bit mode. Okay. Plus I, a number used in floating point instructions when one of the operands is ST. Okay, I'm going to skip that one because I'm not doing a floating point. So register codes associated with the plus R stuff is that, so in my example, I said if we had, if we wanted R9B, then we would set, or let's say R9. If we wanted R9, we would have to set the REX-B. So if we wanted R9, we'd have to set the REX-B bit to be 1. And then the reg field is also just 1. So that would be, 1001. If our opcode was 50, then we would, plus those together. So we would end up with, this is actually REX-B. So we would plus the lower 3 bytes here, so we'd end up with 51, and the REX-B would come before the opcode. Opcode column. In the instruction summary table, the opcode column represents each instruction encoded using the VEX prefix in the following form. I'm going to skip this because I think that's a floating point and SIMD stuff. So I'm not going to worry about those right now. EVX or EVEX is also the same, I think. Instruction column in the opcode summary table. The instruction column gives the syntax of the instruction statement as it would appear in ASM 386 program. The following is a list of the symbols used to represent operands in the instruction statements. So rel 8 is a relative address in the range, basically a byte relative address. Rel 16 and rel 32 are the same things, but 32 and 16 bits. Pointer 1616, these are going to be far pointers. So basically we have the code, the segment selector and the pointer. R8 is one of the byte general purpose registers. Available when using, so in 64-bit mode we can use REX-R to extend the register if needed. 16 is 16-bit ones, 32, 64, okay, those are pretty obvious. Immediate 8 is a byte value again. 16, 32, 64, pretty simple. /IB means a single byte value. I mean, that sounds the same as immediate 8, really. RM8 is a byte operand that is either the contents of a byte register or memory. So R/M means register or memory, and then the number denoting the size. Reg is a general purpose register used for instructions when the width of the register doesn't matter, so this is just any register. M is the same for any memory. M8 is just memory with the size. Let's see, we've got far pointers as well. The ampersand here, a memory operand consisting of data item pairs whose sizes are indicated on the left and right. So this is if we've got a pair of things, they need to be, the left one is this size, the right one is this size. Ignoring binary coded decimal entirely. These are memory offsets, which we already looked at for the MOV instruction. SReg is a segment register where we can specify them using these values. Single precision, okay, not going to worry about that. Word W word integer, operands of FPU integer instructions. ST is the FPU stack, so I'm not going to worry about that. MM is an MMX register. Then we got some, okay, the rest of these are like floating points and SIMD things. Register masks, don't need to worry about those. Okay, I think we're just going to skip over that part now. In the instruction encoding, the ModR byte is represented in several ways in the role it plays. The ModR byte has 3 fields, 2-bit mod, RM mod, and then we got reg, and then we got RM. When all of the bits of the ModR byte have fixed values for an instruction, a 2-hex nibble value for that byte is presented after the opcode in the encoding boxes. If only the ModR mod must be 11 and reg and rm are unrestricted. This is denoted as 11RRRBBB. So yeah, basically it's just telling us how to encode mod rm if needed. Operand encoding column in the instruction summary table. The operand encoding column is abbreviated opn. Instruction operand encoding information is provided for each assembly instruction. Okay, EVX. Okay, I'm not going to worry too much about that one. Okay, so 64 32-bit mode column in the instruction summary table. The 64 32-bit mode column indicates whether the opcode sequence is supported in 64-bit mode, the compatibility mode, or other IA32 modes that apply in conjunction with the CPU feature flag associated with specific instructions. So in the 64-bit mode is the left of the slash and has the following notation. So if we see a V, it's supported, I is not supported, NE is not encodable, NP is that the REX prefix does not affect legacy instructions in 64-bit mode, NI is the opcode is treated as a new instruction in 64-bit mode, and NS is that the syntax requires an address override in 64-bit mode and is not supported. Using an address override prefix in 64-bit mode may result in model-specific execution behavior. Compatibility mode, same stuff. CPU ID, not going to worry about right now. Description section. Summary of terms that may be used in this description. Not bothered about these. Shorthand, so RM field is shorthand for RM and any rex B, and reg field is reg with any rex R. Operations section. So this is related to algorithms written in pseudocode, which I'm not going to worry about at all here. This is still the same stuff. And then we got Intel C, C++ compiler intrinsics equivalence section, which I don't think I'm going to worry about. Flags affected is pretty obvious, so I'm not going to read about that. Protected mode exceptions. I think that will be pretty obvious. Real mode exceptions, floating point, SIMD, 64-bit, doesn't have anything there, AMX considerations, and then we get to the start of the instruction reference. So that's chapter 3 covered. I think now basically we'll just have a very quick look at opcode map. So use, which is Appendix A. Use the opcode tables in this chapter to interpret IA32 and Intel 64 architecture object code. So basically, I think what this is you can use it to look up opcodes that you don't know what the instruction is. So from what I've seen before of this, for example, if we look up the REX prefix one, so in 64-bit mode, REX prefix was range hex 40 to 40, or 40 to 4F. So if we looked up 4, 0 here, so we've got 4, 0, that comes to this place, and that ranges across this entire column here, which goes to 4, 7. And this range in IA32 maps to the inc instruction, and in 64-bit, it's a REX prefix. And if we go and look at the rest of the range down here, this 4 range across the entire thing, all the way up to 4F, in IA32 is the DEC instruction, and in 64-bit mode it's a REX prefix. And I think it said that FF was the code to use in 64-bit mode, which if we do F, and then, this is F, E, and this is FF, these are now the inc DECs that we have to use in 64-bit mode. I don't think this is going to be that useful beyond knowing how to look up some opcodes every now and then, so we'll just skip to Appendix B. So this appendix provides machine instruction formats and encodings of IA32 instructions. The first section describes the IA32 architecture's machine instruction format. The remaining sections show formats and encoding of general purpose MMX, P6 family, SSC, x87 FPU instructions, and VMX instructions. Those instruction formats also apply to Intel 64 architecture. Instruction formats used in 64-bit mode are provided as supersets of the above. So, machine instruction formats, this is basically the same diagram that we've already seen in the earlier chapters. So we have the prefixes, the REX prefix, the opcode, followed by ModR, SIB, displacement, and then immediates. Where this reg1 could be used to extend the opcode. So it could be used to extend the opcode if needed. Legacy prefixes, let's see, is there anything useful here? REX prefixes, 16 opcodes, which makes sense because the low nibble is the only dynamic part. We've already been over how they replace inc and DEC. Opcode fields. The primary opcode for an instruction is encoded in 1 to 3 bytes. Within the primary opcode, smaller encoding fields may be defined. These fields vary according to the class of operation being performed. Almost all instructions that refer to a register and/or memory operand have a register and/or address mode byte following the opcode, so that's ModR and maybe SIB. Certain encodings indicate that a second address must be used, the SIB byte must be used. If the addressing mode specifies a displacement, the displacement value is placed immediately following the ModR or SIB byte. Okay, we already know that stuff. Special fields. Table B1 lists bit fields that appear in certain instructions, sometimes within the opcode bytes. All of these fields, except the D bit, occur in general purpose instruction formats. So we've got reg, we've got WS, sreg. So D specifies the direction of data, see table B11. Reg field, okay, so basically the registers go up in numbers from 0 to 7. So the order is A, C, D, B, SP, BP, SI, DI. Then we have 16 bits, so this is the same numbering, but when the W is 0 and when W is 1 we get different things. So I assume that this is width. W specifies if data is byte or full-sized, where full-sized is 60 SK, so that's just how it selects different registers based on the size. Reg field for 64-bit mode is the same thing, But during 64-bit data operations, it selects these, and those are based on REX prefixes. Same stuff down here, except for this note here where these can't be encoded when a REX prefix is used. Such expressions default to the low bytes of these ones instead. Encoding of operand-size is the W bit. The current operand-size attribute determines whether the processor is performing 16-bit, 32-bit, or 64-bit operations. Within the constraints of the current operand-size attribute, the operand-size bit can be used to indicate operations on 8-bit operands or the full operand size. Okay. Sign extends bit. Okay, whether it's sign extended or not. Segment register field. I don't think we're going to worry about that. Special purpose register doesn't seem relevant to me right now. Okay, let's just skip through a bit. Direction bit. In many 2-operand instructions, a direction bit indicates which operand is considered the source and which is the destination. So we're basically looking at the tables earlier, the ModR and SIB tables, assuming that the first operand is the source, because that's the Intel syntax for the assembly. Where the source, the destination comes first. So the first operand would be the destination. But I guess in many 2-operand instructions, a direction bit indicates which operand is considered the source and which is the destination. When used for integer instructions, the D bit is located at bit 1 of a 1-byte primary opcode. Note that this bit does not appear as the symbol D in the tables. The actual encoding of the D bit as 1 or 0 is given. When used for floating point instructions, the D bit is shown as bit 2 of the first byte of the primary opcode. So let's just copy this out. Keep a note of this. Okay, other notes. Okay, and then we've got just like some references for encodings of instructions. Okay. So I think maybe I'll just end this by looking at manually encoding a MOV instruction and just seeing if it will make sense. So for example, we'll go to M. We'll have a look at the MOV table over here. So let's say that we wanted to encode a MOV to let's say that we wanted to do MOV of an immediate 64 to R64, so a 64-bit register. We would need to do REX prefix with W set. So we would have 0, 1, 0, 0, and then W is the first one. Okay. Then we would have B8. So this is actually 4, 4. So this would be OX, or this would be 4, 4. Followed by B8 plus RD. So RD was an extension to the opcode itself. So let's say we wanted to do ECX, which would be, oh sorry, RCX. So RCX would be the second register based on the counting up that we did in the tables earlier. So if RAX is register 0, then RCX is register 1. So we would have B8 plus 1, which would be B9. Then we would have some immediate oct, which would be the 64-bit thing. So if we said, for example, 7 just the whole way, maybe 7 just for the whole way here. So we could try and encode this. We could try and maybe just assemble this using NASM and then disassemble it to see if this is correct. So we expect 4, maybe B9, and then followed by the immediate. So let's do sublime foo.asm. So we need to set bit 64. So this will be a mov to RCX with some 64-bit thing. So we'll say, why don't we just say 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. And we'll try and do that. So we'll say foo.asm output to out. NASM disassembly B64, and we'll pass in out. We get 48 for the REX prefix. That's because I've miscounted it. So it was actually 0100, which is 4, and then followed by the W bit being set, which is the first one. So that's actually 8. So that was just me miscounting it. So 4, 8, followed by B9, which is what we said, followed by the 8-byte immediate here. So this is the opcode, which was B8. We added 1 to the low 3 bits to select the RCX register, and then we're moving this immediate into it. And the 48 on the beginning is the REX prefix with the W bit set to 1 to make it a 64-bit operation.